Well, greetings, Mr. Kolazar's class. We're going to now move into our limiting reactants for stoichiometric calculations. Now this section is going to be one of the more difficult ones that we work in, so as we're working we need to spend a little bit more time listening and watching the information here. What we're going to do is identify what are limiting reactants in our chemical reactions and identify which one's the excess or the amount remaining afterwards. So during our chemical reactions, something's going to stop our reactions from happening. So we're going to be able to find the mass of our product during our chemical reactions, depending on what we start with. Now, why chemical reactions stop? One reactant in a chemical reaction is going to limit or determine how much product is actually produced. Eventually, one reactant is totally consumed during a chemical reaction, and this is going to limit or stop how much product we can actually produce. Once it's used up, we can't make any more product because our reactants are all used up, or one of them's used up, so at that time the chemical reaction stops. The other reactant, whatever's left over, we're going to have something that's in excess. And what's in excess is what remains after, is left over after the chemical reaction stops. So one of our reactants is going to run out first. Now, chemical reactions stop when one of them is all used up. So one of our reactants, once it's used up, no more product can be produced. So an example of this is when you're driving your car down the road, there are two things that it needs. It needs gasoline, which is octane, and oxygen, which we get from the environment around us. Now this is a combustion reaction that produces heat and energy along with carbon dioxide and water to keep our car going down the road. Now C8H18 is our octane. Is going to determine how far your car can go. When your gas runs out, your car stops. So that's going to be what is our limiting reactant. It limits our chemical reaction because once octane runs out, we can't have any more chemical reaction occur and your car will stop. So the excess reactant is oxygen. It's the one that we had more than enough of during our chemical reaction. Now we're going to abbreviate these LR, limiting reactant, and ER, excess reactant. So you're going to hear those terms a lot throughout this section. Limiting reactions occur when there's two or more reactants. And what will happen is more than likely one of them is going to be used up first and limit the amount of product, because once one of them is used up, we can no longer form any more product. So what we're going to look at are to determine which one is the limiting reactant, or LR. We're going to calculate the amount of product that we can form using the limiting reactant, and we're going to analyze how much excess reactant we have left over. So there will be some of our starting material left over after a chemical reaction. We're going to find out how much it is. I'm going to be giving you this page if you haven't received it already. This page is given to you and you're just going to put it at the bottom of that page 6. So at the bottom of page 6 is where this in your notes is going to go. And it's going to go through our step-by-step process. So part 1, we're going to write the amount and what you are looking for under each substance in our balanced chemical equation. We're going to convert moles, or convert to moles if it's not already in moles of what we have. Now 3 says you can start to visually look at limiting reactants, but B is the one we really want to use. Don't worry about A. So in B, use the mole to mole ratio to convert both reactants to the other reactant. And that's going to be what we need. So we're going to look at both of those. And what we're going to look at is using the mole to mole ratio of both reactants. And we're going to talk about this being the haves versus the needs. So that's going to be our key part here. The limiting reactant, we have less than we need, meaning it's going to run out. The excess reactant, we have more than we need, so there's going to be extra afterwards. And then we're going to be able to use the amount of limiting reactant, which one runs out, to determine the amount of product formed. And remember, we want to be in moles so that we can compare directly mole to mole ratio so that we can move right into our product. Last one, 5, determine the amount of excess reactant left over to use to find out how many moles of ER are left over. So as we're going, you're going to have a certain amount of excess reactant you have, and a little bit of excess reactant that was used. So the difference between those is how much is left over, and we have to be in moles in order to determine how much extra is left over of the excess reactant. So let's use this information to go through our problem at the top of page 8, number 24 in your notes, I believe is where this one is. So the reaction between sodium and iron 3 oxide is one that has a series of reactions that inflate an automobile bag. Sodium plus iron 2 oxide, iron 3 oxide produces sodium oxide and iron. So the question is, if you have 100 grams of sodium and 100 grams of iron 3 oxide, determine the following. Which one is going to be the limiting reactant? Which one is the excess reactant? How much iron are we going to produce? And the mass of the excess reactant that remains after the reaction is complete. So once one of them runs out, how much of the other do we have? So our first step says, number 1, write the amount of what you're looking for under the balanced chemical equation. So we have 100 grams of sodium, 100 grams of iron oxide, and we're asking for how much iron are we going to produce in the end. So one of these two is going to run out first. The one that runs out first is our limiting reactant. The one that is left over afterwards is going to be our excess reactant. So our next step is we're going to convert to moles. So our first one is we have sodium, 100 grams of sodium, and we want to convert grams to moles. So 1 mole of sodium, 22.99 grams of sodium. Remember, that's from the PT. Grams cancel our grams, and we're starting out with about 4.35 moles of sodium. Now, the second one is we have 100 grams of iron 3 oxide. From the periodic table, 1 mole of iron 3 oxide is equal to and again, that's from the PT. So right now we have about that many moles of each substance, 4.35 moles of sodium and about 0.626 moles of iron oxide. So what we need to do is find out how much we need of each one. So at this time, we're going to use the mole to mole ratio to convert both reactants to the other reactant. And that's going to be what we call what we need. So looking at our BCE, 6 moles of sodium to 1 mole of iron produces 3 moles of sodium oxide and 2 moles of iron. So 4.35 moles of sodium. Our mole to mole reaction, 1 mole of Fe2O3 to 6 moles of sodium. Moles cancel moles. Sodium gives us about 0.0 0.725 moles of Fe2O3. And if we're starting out with 6.26 or 0.626 moles of iron oxide, our reaction 6 moles of sodium over 1 mole. Oops, 1 mole. I'll squeeze mole in down below there. So our moles cancel our moles, and if we multiply, we get about 3 moles of sodium. Now this is how much we need in order for the reaction to completely go or to consume all of the other one. So we have our halves versus our needs. So the question becomes, if you have 4.35 moles of sodium and you need 3.75 moles of sodium, do you have enough? 4.3, 3.7, so you have enough sodium in order for this reaction to work. Now, if you have 0.626 moles of iron oxide, and you look up above and you need 0.725 moles of iron oxide, you do not have enough. You have this much, you needed more in order for this to work. So our iron 2 oxide, excuse me, iron 3 oxide is going to be our limiting reactant. When this is used up, our reaction stops. So the excess reactant then is our sodium. We're going to have more than enough sodium in order for this reaction to go. So once the 0.626 moles of iron oxide's up, the reaction stops. So to find out how much mass of solid iron is produced, we're going to use the limiting reactant to find out how much product we can produce. So we have 0.626 moles of iron 3 oxide, and we want to find out how many moles of iron we can produce. So our reaction says that 2 moles of iron is going to be needed to react with 1 mole of iron 3 oxide. Our moles cancel our moles, and since we want to get mass, not moles, we need to go ahead and convert 1 mole of iron into mass. Periodic table, 58.55 grams of iron equals that 1 mole. Moles cancel moles, and we are left in the end with about 69.95 grams of iron being produced. So the mass of solid iron, grams of iron. And our last question says the mass of excess reactant that remains after the reaction is complete. To do that part, determine the amount of excess reactant left over. We're going to use the amount of what we have minus what we used or needed is going to be what's left over. So we had 4.35 moles of sodium. For this reaction to work, 3.757 moles of sodium were used. So if we were to take our 4.35 moles of sodium and subtract it from what we used, we would end up with how much difference or how much excess sodium we had, and that would be in moles of Na. So our 0.593 moles of sodium is what's left over. From there, what we need to do is moles of sodium, 22.99 grams of sodium over 1 mole of sodium is going to give us about 13.63 grams of sodium would be left over after that reaction is completed. Mass of excess reactant afterwards, we'd have about 13.63 grams of sodium. So starting with 100 grams of sodium and 100 grams of iron 3 oxide, we would end up running out of the iron 3 oxide first. We would produce 69.95 grams of iron in the end of this reaction, and we would have 13.63 grams of sodium left over afterwards. That was a lot of information. You might have to go back through and look at this problem again. I would like you to try out problem 25 using our information from our handout and from using our information from our last one. Once you've completed it, you need to show me your work. The answers in the end I'm going to give to you now. So, balanced chemical equation, 6 carbon dioxides plus 6 waters will produce 1 sugar, glucose, and 6 oxygens. Now, as you work through this problem, 88 grams of carbon dioxide and 64 grams of water are available for this reaction. In the end, what you need to do is, showing your work, you should come up with similar answers to our limiting reactant and excess reactant, and the amount of mass produced should be close to 60.0 grams of glucose, and our mass of the excess reactant that we'll have left over is there. So you need to show me how you got all of these answers, and should have comparable answers afterwards. Check with me with any questions on that part. And so our last little part for chapter 11.3, why do we need to use excess reactants? A couple of reasons are going to help us out. First off, if you have excess reactants, it'll make sure a reaction goes to completion. A lot of times it's always best to use your cheaper reactant in excess, so that as you're going, you make the product you want, but then you spend less money on the more expensive reactant. And 3, we'll talk about later on in a future chapter, more reactants will actually speed up the reaction because there are more possible chemical reactions that can happen. That'll end our 11-3. Make sure you re-look over this section so that you can see any questions that we have, breaking down step by step with each one.